This video is a short introduction to the inverse sine function. Quickly reviewing, remember, not every function has an inverse that is also a function. We're going to need the horizontal line test for inverse functions. This says a function has an inverse that is a function if there is no horizontal line that intersects the graph of the function at more than one point. Functions that pass the horizontal line test are called one-to-one functions. So right now, let's take a look at the graph of f of x equals sine x. It is graphed here in blue. And is this graph going to pass the horizontal line test? Well, if I bring a horizontal line down, how many times is this horizontal line going to cross the graph? Many times, in fact, an infinite number of times. So f of x equals sine x is not a one-to-one function, and its inverse will not be a function. So in cases like this, we have to restrict the domain. So limiting the x values over which my graph is plotted, can see that my graph is being plotted over less and less x values. But notice it is still not one-to-one at this point. But if I restrict it even more, now if I take my horizontal line, it's only going to cross the graph one time. So now I finally have restricted the domain so that I have a one-to-one function. So the restricted domain goes from negative pi over 2 to pi over 2. And that gives me a range of -1 to +1. So now this function with the restricted domain has an inverse that is a function. So to graph it, we need to draw the line y equals x, and the graph of a function and its inverse are reflections about this line. So if I reflect my blue graph about the line y equals x, I get the red graph, which is the graph of the inverse sine function. And remember, the range of a function becomes the domain of the inverse, and the domain of a function becomes the range of the inverse. Now, the inverse sine function can be written two different ways. The first way is y equals sine with a -1 exponent of x. This is red, y equals the inverse sine of x. Or it can be written as y equals arcsin of x. These two statements mean exactly the same thing. Now remember, the domain or the input values are the trig function values that lie between -1 and 1. And the output or the range values are the angles that give this trig function value, and they lie between -pi over 2 to pi over 2, including both the endpoints of the interval. So my output can either be a positive angle anywhere between 0 and pi over 2, or it can be a negative angle anywhere from 0 to -pi over 2. And instead of using the variable y, it is often easier to use theta because we associate that with an angle. Now, looking at a couple of examples, I need to find the exact value of, in A, the inverse sine of the square root of 3 over 2. To start with, it might be easier to set this equal to theta. And remember, translate it. What does this mean? This means that the sine of theta equals the square root of 3 over 2. But not just that, I also have to include the restrictions that theta must lie in the region of -pi over 2 to pi over 2. The reason we need to put this in there is because how many solutions are there to the sine of theta equals the square root of 3 over 2? There's an infinite number of solutions to this equation, but there's only one solution to this problem because my solution has to lie in this interval. Now I'm restricted to quadrant 1 and quadrant 4. My sine value is positive. Remember, the sine is the y-coordinate. The y-coordinates are positive in quadrant 1, negative in quadrant 4. So my answer must lie in quadrant 1. And what angle has a y value of the square root of 3 over 2? Here's the square root of 3 over 2. So here is the angle that produces this. So the inverse sine of the square root of 3 over 2 is equal to pi over 3. Or if we wanted to work in degrees, that is 60 degrees. In part B, we need to find the arcsine of 1.5. But remember, the domain of the arcsine or the inverse sine function is negative 1 to 1. Is 1.5 in this interval? No. Therefore, the arcsine of 1.5 is undefined, because there is no angle whose sine function equals 1.5. And in the last example, I need to find the exact value of the inverse sine of negative 1/2. Set it equal to theta. And what does this mean? This means that the sine of theta has to equal negative 1/2. But don't forget the restriction, and theta must lie in this interval. So I have to be somewhere over here on the shaded region of my unit circle. The sine value is negative. That means I need a y value is negative. Y is positive in quadrant 1. So my answer has to be in quadrant 4. And here I have the y value of negative 1/2. So here is the angle I'm interested in. And what a lot of students do is they just go, okay, theta equals 11 pi over 6. And can't understand it when they get the question wrong. But is 11 pi over 6 in this interval? No. I need the angle that rotates in the negative direction. Sometimes you can figure this out in your head, but if you can't, just think of coterminal angles. I'm going to take 11 pi over 6 and I'm going to subtract 2 pi from it. So I need a common denominator of 6. So I'm going to multiply this by 6 over 6. So I'm going to get 11 pi over 6 minus 2 times 6 is 12 pi over 6. So what's my answer? 11 minus 12 is negative 1, or just negative pi over 6. So the inverse sine of negative 1/2 equals negative pi over 6. Or if you're working in degrees, that'd be negative 30 degrees. So be very careful with inverse sine problems when the answer is in quadrant 4. You can't read the angle immediately off the unit circle. You need a negative angle as your answer.